All right, now we learned many theorems on the set families with intersecting properties, and in this chapter I will show you two applications of those theorems in geometry. Right, so the first problem is about the chromatic number of the plane, or Rn, this space. All right, so what we do is the following. Imagine that, let Gn be the graph on Rn such that two vertices, 2 points, these are vertices, are adjacent in Gn if and only if their distance is exactly 1. Okay, I should have said that 2 points are xy. Here the number of vertices is infinite, right? But we can still define such a graph. Now the question is, what is the chromatic number of Gn? For those who never heard of chromatic number, let me briefly say what it is. I guess most of you already know what chromatic number is, right? So the chromatic number of graph G is the minimum K such that G has a K coloring, where the K coloring, sometimes called proper K coloring, is a function from vertices of graph to 1 up to K such that adjacent vertices get distinct color. So the chromatic number is a minimum such K. So you may wonder, well, maybe is it even defined, right? Is the chromatic number of the whole thing, is it even defined? And I will show you why it is defined. But first of all, you may wonder why this is a well-defined problem. And this is due to the following. So this is due to the Rusin and Erdős in 1951. So let G be a graph and K be an integer, and if every finite subgraph of G has a K coloring, then G has a K coloring. So this is what's called the compactness of the chromatic number. All right. So for instance, let's look at the G2. So G2 is the chromatic number of the plane, or sometimes this graph is called unit distance graph. Oops. Right. So even though the plane has infinitely many points, if the chromatic number is at most K for every finite subgraph, then the whole graph has a chromatic number at most K, right? So the problem of determining the chromatic number of the plane reduces to the problem of determining chromatic number of the finite subgraphs of the unit distance graph of the plane. And this problem, so let me start with the original problem. So what was the initial problem? What is the chromatic number of the G2? Okay, let's just say chromatic number of Rn as the chromatic number of Gn. Okay, so what is the chromatic number of R2? The plane. This problem was proposed by Hadwiger in 1944 and Nelson again around 1950. So Hadwiger was a German mathematician, and Nelson was an American mathematician who was a professor in Princeton University for a long time, since he was 20s. And once, when I was a graduate student, there was a talk by Alexander Soifer, who gave a talk on the history of this problem. And he was tracking down the origin of this problem. And in the end, he concluded that Nelson was one of the origin of this problem. And there was like early 2003 or something. And in the audience, there was a Nelson, but he doesn't remember whether he made a problem or not, because he was now, at that time, he was an old man already. And this was when he was very young, like probably 20s. All right, so now what's known? So first of all, chromatic number of the plane is at most 7. Now how do we know that? I'm gonna fill the plane by the hexagons. Let me try. But each hexagon has diameter slightly less than 1. Right? And then I'm gonna color everything here with the same color. So let's say color 1, 2, 3, 4, 5, 6, 7. And this is the way. I mean, the thing is, oh no, maybe I need to have a diameter a bit bigger. Right. So what's the diameter I want? I want no 2 points of the same color to be adjacent, right? So how do I pick the, right? So if this is 1, so no 2 points here have color distance. Yeah, so the diameter of this guy is slightly less than 1. And if this is 1, I want something like this to be 1. Right? So that these two have no 2 points of distance 1. And so I fill probably same way, right? So I want to fill the plane. So 1, 2, 3, 4, 5, 6, 7. And then I fill here 1, right? So 2, 3, 4, 5, 6, 7. So this is the pattern. Is it clear? Right. So now, like, same thing appears here, here, and then so you go 2 and below, and then 2 and below, and right. So that's it. And then any 2 points here has distance bigger than 1. And you can easily check that this is the proper coloring. Okay. And for a long time, this was the only bound known. Chromatic number of the plane is at least 4. Well, I can easily say that it's at least 3, because if I have a triangle whose sides have the same length 1, then all 3 points have distinct colors, right? Now, I add another triangle here, then these 2 points, if the chromatic number is 3, then these 2 points must have the same color. Now what I do is find the point here with the same distance, so this has same distance, then attach a gadget like this, right? So this distance is 1, and this is what? Maybe square root 3, right? Then x, y, z. So the color of x has to be, if the chromatic number of R2 is 3, and if this is colored by 3 colors, then color of x is equal to color of y, which is equal to color of z. But then x and z have the same color. That's contradiction, because these 2 points have distance 1. And for a long time, this was the only known lower bound until 2018. The Aubrey de Grey proved that chromatic number of R2 is at least 5. And there was a big news in 2018, so I can show you the news article about it. Yeah, this was Quantum magazine, so you can find it. This was discovered 60 years after the problems were proposed. And the title of the article is Decatur Problem is the amateur mathematician. So, and you see this graph. Here's the graph. 826 vertices. This graph requires at least 5 colors. So these are points on the plane that if 2 points of distance exactly 1 should have distinct colors, so you need 5 colors. And this is interesting article, and you can have a look. Right, so in the article it says, Aubrey de Grey is a biologist known for some weird claim, but he posted a paper on the archive, and people were surprised that this is actually correct proof. All right, now let's go back. Now our question is about the chromatic number of Rn. So why is it bounded? First of all, why is it bounded? How do we even know that it's bounded? Right? Let's imagine that I partition the Rn into cube, where each side has length square root n. All right. So partition Rn into cubes of whose sides have length square root n. Okay, so, and then what I do is inside each part I will take I right, so we wanna yeah, so yeah. And why do I care? Because yeah, I mean the thing is the length, the diameter of this, okay, side whose side have length slightly less than, okay, square root n minus epsilon, right? Okay, now then if you look at this 1 over square root n, how far can you have? I mean, how many intervals do you have in distance and most 1? Well, I mean, the thing is, I can choose colors. Let's say if it's R1, no, not R1, but if I split the real line by an interval of length square root n minus epsilon, then for each interval, like this interval, I will, let's say, color 1, 2, 3, 4, and then so that my goal is to say 2 points of the distance and less than 1 in a different interval. I mean, the distance and most 1 in a different interval must have distinct colors, distinct numbers. So we could probably get something like a square root n plus 1. So that many, I may need this many numbers, and then I rotate, right? So 1, 2, 3. So how do I explain? So for each axis, I partition it into the intervals of length square root n minus epsilon. Oh, I don't need a minus epsilon because, okay, let me, as long as I make this type of interval where this point is contained, right? So x and x plus 1 over, oh, side length has 1 over square root, 1 over square root. Yeah. Right? As long as I have a interval like this, and then if I pick one interval there, then I have some cube in array, right? So for each axis, I choose small interval of length 1 over square root n, but you don't have a diagonal, right? Because the bigger side is not contained. So diameter of this is like you don't have 2 points inside this cube of distance exactly 1. Right? Now, the color of this cube, I colored this whole cube by the tuples of numbers, right? So for each axis, I have some number, like 1. If this is 1, 2, 3, then the color of this cube is 1, 2, 3. So this naive argument gives you that the chromatic number of the plane Rn is something like you need the square root n plus 1 colors for each interval on the axis, and then you have n's power. So this is about like e to the half n log n. Right, with some errors. Now, so this is not a, so growing faster than exponential function. But anyway, for any fixed n, this is an upper bound, and therefore there must exist some kind of finite number k such that chromatic number of Rn is at most that constant. Now, here's the theorem. So instead of n log n, we can reduce to n. Chromatic number of Rn is at most 9 to the n. Why? Okay. Now let x be a maximal set of points in Rn such that distance between any 2 points is at least half for every distinct point xy in x, right? So the x is definitely a infinite set. I want to choose a maximal set that I cannot add any more points in order to meet the distance condition, right? So this means that the union of all the balls of radius half covers Rn. Because it misses some points, then I can add it. So this is the open ball of radius half, right? Set of points of distance and more, less than half from x. And moreover, the ball of radius 1 over 4 for all x in the x are disjoint because any 2 points have distance at least half. So what's the goal? We color b of x half by the same color. So all points in the same ball from x of radius 1/2 have the same color, so that these 2 poles have distinct color if the distance between them is less than 2, right? So if these 2 are x and y, I'm coloring all the points of here with the same color, and if these 2 balls have the same color, if these 2 balls have distance less than 2, then they must, if this is less than 2, then there are 2 points whose distance is exactly 1. So I want to make sure that this doesn't happen. So in this case, this one and these balls have distinct colors. That's what we want. So now this is an easy argument. Then yeah, you know, one of the typical argument to prove the chromatic number is small is to prove that maximum degree is bounded. So what is the maximum degree? Of this graph, right? So in other words, what is the number of what is the upper bound on number of pores? Okay, number of points such that y is in x and distance xy is less than 2, right? And now we use the fact that both of radius 1 of 4 are disjoint. So the number of, so degree of x, okay, so G is the graph defined on x where 2 vertices are adjacent if their distance is less than 2. This is, well, this plus 1. Well, these are the number of balls that inside, right? So if the distance is less than 2, so this is, if this is x, but each ball has a radius 1 of 4, right? So I look at this picture, and then inside I have a balls of radius 1 of 4. So what is the maximum number? So that's the volume of 4 of radius 2 plus 1 over 4. So 4, 9 over 4 divided by volume of ball of radius 1 over 4. Right? Because these balls are contained in ball of radius 2 plus 1 over 4, and each ball has a radius, the balls of radius 1 over 4 are disjoint. Now this is, this ratio is this thing, right? So it's 9 to 10. Okay, so that gives you an exponential upper bound. And so this is improvement, but easy improvement. We didn't do anything. The best known so far, I'm not sure whether it's best known, but there's some research by Lam and Rogers, 1972. They proved that Rn has chromatic number at most 3 plus literal 1 to the n. Now this is easier side because for the problem on chromatic numbers, typically it's easier to find an upper bound by coloring. Now the more difficult problem is to find the lower bound. That the chromatic number cannot be too small. That means no matter how you try to color, there must be some problem. And that's the theorem that has interesting proof. This was due to Frankel and Wilson in 1981. They proved that for large n, the chromatic number of Rn is at least 1.2 to the n. So how do we prove that? So one of the key technique to prove the lower bound on the chromatic number is the following. The chromatic number times alpha, the size of maximum stable set. Let me so this is the key idea. So this, what is alpha of G, is the maximum size of an independent set, where the independent set is a set of vertices such that no two vertices are adjacent. So why is this useful? Because if we have an upper bound on alpha, then so any upper bound on alpha will give a lower bound, right? So what we want to do, so the goal is construct some finite set of points in Rn such that any set any subset whose pair of points have distance not equal to 1, but instead of 1, we can just fix any number, fix the constant, right? Because I can scale, right? I can scale, I can multiply some number to the whole picture, has a small size. So that means I have some subgraph of the whole space where this subgraph has a large chromatic number, and therefore whole graph has a large chromatic number. And this subgraph has the property that any independent set has small size. So the alpha is small, so therefore chromatic number is large. All right. So that's the goal. So we need to find the set of points in Rn so that no two have distance exactly something. Set of points in Rn where any set whose set of points, whose pairs have distance not equal to something, will have a small size. And that's where we're going to use L-intersecting theorems about L-intersecting families. Okay? So choose a prime P less than n/2. Now I'm going to map a subset of 1 up to n to the Rn. Right? So you have just by characteristic vector. Right? So if I have set A, then set A is mapped to the Z1 vector. Right? So let's say this is phi of A. Now what is the distance between phi of A and phi of B? If you have two subsets A, B in N, the distance between these two is the square root of sum of the differences, right? Sum of the squares of differences, right? So let me, like for instance, ai minus bi squares, but that's exactly the symmetric difference squares. So if both a and b have size, let's say 2p minus 1, then the distance between the a and b in the images is a delta b, square root of a delta b, but that's the same as a minus a intersection b, but a is 2p minus 1. Oh, that's twice of that. Yeah, I mean more precisely, it's, yeah, that's a plus b minus twice of that. So 4p minus 2 minus twice a intersection b. Right? So the distance depends on the size of intersections. So for instance, if a intersection b is not equal to b, that is the same as saying the distance between these 2 points are not equal to 2p minus 2. All right, so that's the setting. So we want to find the set of points. Okay, so let GP be a graph on subsets of size 2p minus 1 of 1 up to n, such that two vertices A, B are adjacent if their intersection has size p. All right, so their intersection is size p, and therefore the chromatic number of GP is definitely lower bound of chromatic number of Rn, because I can map all the vertices to the points on Rn, and if 2 points have intersection exactly p, 2 vertices have intersection size exactly p, that their distance is exactly square root of 2p minus 2. And if the intersection is not p, then distance is not square root of 2p minus 2. And then in this image, I can scale everything by a factor of 1 over square root of 2p minus 2, then everything is normalized, right? So it's a subgraph. GP is a subgraph of graph or unit distance graph of Rn. Now we need to find the upper bound on alpha. Now what's left is find upper bound on alpha of GP. So what is upper bound, right? So it's an independent set. It's some family of subsets of size 2p minus 1 in 1 up to n, such that for all x, y, and f, the intersection has size different from p, right? And that's where we use theorem of Alon-Babai Suzuki. So use Alon-Babai Suzuki. So let's take L to be not 0, 1, 2 up to p minus 1, and then now check the condition. Let's check the condition. In order to use Alon-Babai Suzuki, I need to make sure that each set has size not in L. Here each set has size in L, right? Each set has size 2p minus 1. So it's better to avoid p minus 1. Let's avoid p minus 1. So what it mean? If it's not p minus 1, then it's 2p. Right. And intersection is not p minus 1 if and only if the images have distance square root 2p. So then subsets of size 2p minus 1, then this is not p minus 1. Alright. Okay, that's change. Then instead of this, I put 0, 1 up to p minus 2. Alright, now looks better. Then for any member in the family, the size of that is 2p minus 1, which is not in L modulo p. And any intersection, for any pair, the intersection has size not p minus 1, and the intersection will not have size 2p minus 1, right? Because the intersection is less than 2p minus 1. So we can say in modulo p, any intersection is in L plus pz for all distinct fy. So this means by Alon-Babai Suzuki's theorem, size of f is at most n choose the number of n choose s. S is p minus 1. All right. All right. So the alpha of Gn, no, it's not Gn. What is the name of the graph? Gp. The alpha of graph Gp is at least, so at most this one. Therefore, the chromatic number of Gp is at least number of vertices, which is n choose 2p minus 1, divided by number of divided by the maximum size of stable set, which is n choose p minus 1. So this is alright. Let's do something. Do you remember? Do you know this inequality? N choose k is equal to n over k times n minus these equations. So I'm gonna apply that. So just to simplify the computation, so n plus 1 2p, and then n plus 1 p. All right. Then I can cancel these two. So this is equal to twice n plus 1 choose 2p divided by n plus 1 choose p. And now what's left is to approximate this thing, and we're gonna use a Stirling's formula. Right, now we're gonna use a Stirling's formula, and we need to choose N and P in an appropriate way. So n factorial is square root 2 pi n and n over 2 to the n and some error term. And from here, if you have n, choose alpha n, then this is n factorial and n minus alpha n factorial and n minus alpha n factorial, right? And then it's gonna be square root n and square root 2 pi and square root alpha and square root 1 minus alpha n, right? And then yeah, so n over e to the n divided by alpha n of e to the n alpha n and 1 minus alpha n over e to the 1 minus alpha n and some error term. And now once we cancel everything out, then it's square root 2 pi and alpha times 1 minus alpha square root and square root n, right? And of course I need a 1 plus literal 1, and here n to the n and n to the alpha and n to the 1 minus alpha n cancel each other, so what's left is right, n to the n, n to the alpha and n to the 1 minus alpha n cancel each other, so alpha to the alpha n and 1 minus alpha to the 1 minus alpha n, right? So this is square root n, and now e to the, right, what you get is alpha n log alpha plus the minus and n 1 minus alpha n log 1 minus alpha. Alright, now the asymptotics of this function depends only on this part. Oh, I forgot to add n. Oh yeah, it is n. So let me summarize. 1 plus little o1 and square root 2 pi square root alpha 1 minus alpha 1 over square root n e to the minus okay, let me just say h alpha, and where h alpha is minus alpha n log alpha minus 1 minus alpha n log alpha log 1 minus alpha. And this is the term that is most important. Right? So what is our goal? Our goal is n plus 1 choose p divided 2p divided by n choose n plus 1 choose p. So this is going to be something like, in order to maximize this, we need to maximize h2 alpha minus h alpha, where alpha is n plus 1 over p. And then now this is the time where you use calculus. right? So H2 alpha. So find the alpha such that H2 alpha minus H alpha is maximized. Use derivative, right? So we take derivative and then find what is it? So this H2 alpha minus LG alpha, and take derivative and make it equal to 0. Then when you get, so I'm not gonna show you all the steps. When you get this alpha, it's gonna be something like this. Right? So for large n, choose alpha such that the n plus 1 of alpha is very close to, no, n plus of 1 over p is very close to this number. And for this alpha, and why can we do this? Why? How do we choose a prime such that the ratio is precisely as we want? Well, the thing is, there is a prime between any two. There is a prime p between k and 2k. I think wasn't this Chebyshev theorem? I forgot. There's a theorem in number theory, right? So any number and twice that, there's something. But anyway, we need actually a better theorem, right? Instead of that, so there is a prime between k and 1 plus epsilon k, if k is large. So if n is sufficiently large, then there is some prime between n plus 1 over 0.146 and n plus 1 over 0.145, for instance, right? All right, and that will give us that the alpha of, so twice n plus 1 to p choose n plus 1 choose p is gonna be at least some number times 1.2 to the n. Oh, why 1.2? Right? Because h of alpha, with the delta alpha, h of alpha is gonna be bigger than 1.2071 to the n. So this is definitely bigger than 1.2 to the n. Oh, no, h of alpha is this. No, actually, what? No, not this one. E to the h of alpha n is bigger than. Yeah, this is what we. So that implies that, and then you may wonder what happens with the constant in front of it, right? So these things. You have a 1 over square root n, blah blah blah, but it doesn't matter, because anything like 1 over square root n and constant, this is all occupied by as long as n is large, this is true, whatever that is, right? Because if you divide this both sides, I mean exponential function is a lot faster, right? So the left hand side will dominate anyway. Okay. Yeah, this calculation is always ugly part, but that's the proof, right? So alpha. So this implies that the chromatic number of G Rn is at least 1.2 to the n. Yeah, for Rajan, not every n, but for Rajan. So it's nice that in a sense that the upper bound is also exponential function, and the lower bound is also exponential function. All right, that's it.